All right, welcome. Today, we're going to unpack the hidden logic that pretty much powers our entire world, the parallel circuit. It's the secret sauce that stops one little failure from causing a total blackout in our homes and all our gadgets. So, let's dive right in. I mean, really think about it for a second. One light bulb in your house finally gives up, but the TV, it keeps playing, the fridge keeps humming, every other light is just fine. So, how is that even possible? Well, it's not magic, it's physics, and it's the exact mystery we're solving today. So here's our game plan. First, we'll nail down what a parallel circuit even is. Then we'll cover its 3 golden rules. After that, we'll tackle some of the math, see a circuit in action, and finally wrap it all up with why this stuff really, really matters.
Visit youtube.com/avidsystem and don't forget to subscribe.
Okay, so that big question about the light bulb, the answer starts right here, with this fundamental idea of what a parallel circuit actually is. You know, it all comes down to giving electricity a choice. And this right here is the absolute key. See, unlike a simple single-file line, a parallel circuit creates multiple branches, multiple paths for the electrical current to travel down. Think of it like a highway that splits into several different lanes. The traffic, which is our electricity, can flow down every single one of those lanes at the same time. Okay, and this slide just lays it all out, right? On the one hand, you have a series circuit. Think of those old school holiday lights. Everything's on one single path. If one bulb breaks, it creates a gap, and the whole string just goes dark. But in a parallel circuit, a break in one path doesn't stop the show. The current just says no problem and uses the other available routes to keep on going. And that is the brilliant solution. Okay, so we've got these multiple paths, but how does electricity actually behave when it's in them? Well, it's not chaos. It follows 3 very specific, very predictable rules. Let's get into what I like to call the rules of the road for any parallel circuit. All right, rule number 1. It's simple, but it's super powerful. Voltage stays the same across every single branch. Imagine a city water main, you know? The pressure, that's our voltage, is going to be the same at every single house that's connected to it. Same deal here. In a parallel circuit, every component gets the full independent source voltage. That's absolutely crucial for consistent performance. Okay, what about the current? Well, think of a river that splits into a bunch of smaller streams. The total amount of water flowing is just the sum of the water in each of those individual streams, right? It's exactly the same for electricity. The total current from the source splits up, and if you add up the currents in all the branches, it equals the total that went in. This idea is so fundamental it's got a name. Kirchhoff's current law. It's a cornerstone of all this stuff. And finally, we get to resistance. And this is where things get a little strange. The total resistance isn't a simple sum. Nope. We have to use this formula with reciprocals, 1 over the value. And the result you get from this is super counterintuitive, but it's also the secret to its power. So let's actually tackle that formula. And don't worry, it's not nearly as scary as it looks, and it reveals something totally fascinating about how these circuits work. Right here, this is the big aha moment. Every single time you add a new path in parallel, the total resistance of the entire circuit actually goes down. Why? Well, because you're giving the current more options. More lanes on the highway means less overall traffic, right? It just makes it easier for all that electricity to flow through the whole system. So, how do we actually do it? It's really just a 4-step process. First, you take your resistors. Second, you flip them to get the reciprocal. Third, you add all those fractions or decimals together. And fourth, and please do not forget this last step, you flip that final answer back over to get the total resistance. Just look at how this plays out in real numbers. With one 60-ohm resistor, your total resistance is, 60 ohms. Makes sense. But add a second identical one in parallel, and boom, the total resistance drops to 30. Add a third, and it plummets all the way down to 20 ohms, which, if you notice, is less than the resistance of any single path. Wild, right? Okay, theory is great and all, but let's make this real. It's time to put our 3 golden rules and our new math skills to the test. Let's solve a quick problem. So here's our setup. All the values are right here for you. We've got a 24-volt power source, and it's hooked up to 2 different resistors in parallel. So that electricity has 2 paths it can take. One way goes through a 10-ohm resistor, and the other way goes through a 20-ohm resistor. So the big question is, how much total current is being pulled from that power source? Now, an engineer would look at this and just break it down using the rules. We know the voltage, we know the individual resistances. So where do you even start? Okay, let's just walk through this using our rules. First, rule number 1, voltage is constant. So both resistors get the full 24 volts. Now we use Ohm's law on each branch by itself. The first branch, with a lower resistance, draws 2.4 amps. The second branch, with higher resistance, draws 1.2 amps. And finally, we use rule number 2. The total current is simply the sum of those two branch currents. And that gives us a final answer of 3.6 amps. That's it. That's the total amount of current flowing out of the source to power both of those components. See, when you follow the rules, it all just falls into place. We've covered the what, we've covered the how, but now it's time for the most important part, the why. Why do we even bother with all this? Well, it turns out the properties of parallel circuits are pretty much what make modern life possible. And boom, here it is, all tied up in a neat little package. Components operate independently. That is our light bulb example, right? Every outlet in your house provides a consistent, steady voltage. And you can easily add more stuff to the circuit. That counterintuitive drop in resistance, that's the real magic. It means you can add more and more devices without making it harder for the whole system to run. It's why our houses are wired this way. So, we've come full circle. The mystery of the burnt-out light bulb, it's solved. It's all thanks to the elegant, powerful logic of the parallel circuit. So the next time you plug something into a power strip, you'll know the secret of the multiple paths that make it all work. The only question left is, where else are you going to spot this amazing principle in action?
Thanks for watching.